Hello students, in today's class we are going to learn applications of refraction. In last class we have already learned what is meant by refraction and its terms, and also laws of refraction, finally refractive index, relative refractive index. And now we are going to learn where does the reflection exist and what are their applications. You see, there are a lot of applications around our world regarding this word refraction. For example, when we place a stick vertically straight into water which presents in a glass tub like that. See, in a glass tub we pour some water like this and vertically we place the stick. We know it's a linear stick and is placed straight. But how does it appear? Let's see. It appears vertical when it is in the air, but it appears like this when it is in water. Why is? Because we are watching the stick from air, and the stick part which is in the air, it appears in same position. Reason is in this position the light is not taking refraction. How? Because this portion is in the air and we are watching it from air. So medium has not changed. There is no bending moment of light. But when we see this portion, it is inside the water. We are watching it from air, but the material is in water. There is change in the medium. When the medium changes, the speed of light changes and its direction also changes, so that it appears to be bent. So not only in this case, this kind of examples many are there. Even into the same tub containing water, when we drop a coin of 1 rupee, so we drop it vertically, but it appears to be falling outside. So it's actually falling vertically down, but we feel it's moving to another corner. And even at the bottom also it appears at another place, not where it is actually exists. So where it actually exists, in such a place we cannot feel it. We feel it, it is existing in another place. So this is also due to the refraction. Even in some kind of ponds, rivers, we can see the water, we feel it is less deeper, but when we jump into it, the water will be very deep. So reducing depth of water is also due to refraction of light. Okay, these are common applications. Okay, regular applications. There is a different application due to change of medium. So let us see that. How can we explain it? Just take an interface and Above, assume it is a denser medium. Below, assume it is a rarer medium. And this is normal. Let us incident a light ray with certain angle of incidence. So we watch carefully, we need to watch this diagram. How does the light is propagating? The light is propagating here from denser medium to rarer medium. So in previous class we have learnt when light travels from denser medium to rarer medium, it is going to bend away from the normal. That means here in this case, compared to angle of incidence, the angle of refraction will be maximum. Okay, we don't stop it here. We start increasing the angle of incidence. So what's the result? No doubt, even at a greater incidence, light is still traveling from denser to rarer medium. Light is still traveling from denser to rarer medium, so that the refraction is again away from the normal. Like this, when we start increasing the angle of incidence, at one point the refracted ray can remain on the interface. That means what we can say here, the angle of refraction R is going to be 90 degrees. At this angle of refraction 90 degrees, whatever the angle of incidence is going to be called critical angle. So critical angle has two definitions. Number one, the angle of incidence where the refracted ray remains on interface. Another definition is the angle of incidence where angle of refraction remains 90 degrees. This is a critical angle. Okay, it is a critical angle. There is still some space beyond this critical angle. If beyond this critical angle we incident a light ray, what would we expect? As expected, it still takes greater compared to the normal, and this greater feels what? The light ray, instead of rarer medium, is getting back into the denser medium. So this is the incident ray and this is the refracted ray. Once again we can check it in another diagram. So this is the incident ray beyond critical angle. Then the refraction would be into the same medium. Okay, the refraction looks same into the medium. What kind of refraction we can call this? This is called total internal reflection. In short terms, TIR. In short terms, it is called TIR, total internal reflection. This is a special effect that you usually find in case of refraction. This total internal reflection also has some uses in our daily life, some applications in our daily life. Where, see some words. First one, mirage. Second, shining of diamonds. Third case, shining of diamonds is the second. Third case is optical fibers. These are some examples of total internal reflection. Let us see how this is going to be happen. You first in mirage. Mirage is an optical illusion. It is an optical illusion. So it is an illusion. It's not real. It's just we feel like real, but it is not real. So like what? On the road surface on hot day, we can see the existence of water. When we walk along the road during summer, far length of the road, at the far distance of the road, we can find the existence of water. But there we reach, whenever we reach that point, there won't be any water traces. Why? Because this is an illusion of water which is created by total internal reflection, which is called mirage. Let us see how is this going to happen. You know, our atmosphere, this is all our atmosphere. It is existing with air. So everyone knows our atmosphere is completely covered by air, but very few of them knows that this air is separated into layers. Why is when sunlight, see, I said mirage is formed on hot sunny day. Why? I also said it is formed during summer. Why is during summer the temperature in our atmosphere is very large. What is this going to make? See, this will separate our atmosphere into layers. Why is when sunlight falls, it reaches the ground part. It reaches the ground part. When falls on the earth, along with the earth, the air in the ground part also gets heated. So this is what? Hot air. You know, when the basic principle of calorimetry, when a substance is get heated, it expands. So when this air is get heated, the particles in it always move. The particles in it move away with each other, and the hot air get expands. So this indicates it is a rarer medium. This indicates it is a rarer medium. And this is, you see now, the upper portion. This is an upper portion. it is not going to get heated, so it is always cold, and for the cold the particles remain closer and it will be a denser medium. Now you see it is a perfect weather condition to get total internal reflection. Why is sunlight always come from the above surface? That means it needs to travel definitely from denser medium to rarer medium. When it travels from denser medium to rarer medium, the incidence when it is beyond critical angle, the straight incident ray take total internal reflection and will be sent back. This light ray, when which is sent back, it creates straight to it on the ground. It creates an illusion here, and we call this mirage. It is the total internal reflection in case of mirage, an illusion creation. This is one application. See next application, diamonds. You know, diamonds refractive index 2.42. Refractive index of diamond is 2.42. It is the highest refractive index for an object which is existing on the earth, on the earth. So due to its high refractive index, it is going to achieve its critical angle very easily within less than 24 degrees. Yes. Critical angle is nearly 24 degrees only for the case of diamond. That means if the angle of incidence is greater than critical angle, definitely the diamond is going to take a total internal reflection. How? See, the diamond. So diamond is definitely denser when compared to air. So when light ray is incident towards the diamond, you see now rarer to denser. So definitely refraction takes place and the light ray enters into the diamond. But next what? Diamond is a transparent and is a denser because it is outside we have air. Now when it is happen from denser to rarer, the light ray takes a total internal reflection due to greater refraction. Angle of incidence is greater than critical angle, so the light ray takes internal reflection and will be sent back. And when it reaches the next surface, there same thing, denser, rarer. So once again it will take a refraction, will be sent back like this again. So like this inside the diamond, every time when the light ray hits the surface, denser to rarer. Due to this reason, it will take total internal reflection. So the light gets stuck inside the diamond and it shines more brightly. It is diamonds. And the last one is optical fiber. So optical fiber is a communication fiber used in today's science and technology, is covered by sheet, core, and at the center we are going to have thin fiber. Fiber is a hairy material made of either glass or plastic. This airy made transparent material lies in the center. When light ray is incident, the incident ray easily enters inside but will not come outside because the fiber is a denser medium and is compared to outer atmosphere, and the light is definitely enters inside beyond its critical angle, so that it will take multiple times the total internal reflection and take multiple reflections continuously and reaches the other end. This is called total internal reflection and a fiber optic communication. It is fiber optic communication. Fiber optic communication. Okay. Okay, students. This is application of these are the applications of total internal reflection. Okay, and we start the class today, and in next class we are going to discuss about glass slab. Sorry, before that we forgot one more thing. We have Snell's law. So in next class we discuss about Snell's law and its equation derivation. After that we are going to learn the glass slab and its activity. Okay, in next class Snell's law derivation and an experiment to prove Snell's law. Okay students, this is the end of session. Thank you.